This is Andrew. We both work as engineers in our applied AI team here at Anthropic. And the kind of topic for this session was inspired by a blog post we put out just a couple of weeks ago, actually, about how to think about building agents that can actually run for really long, extended periods of time. You know, we're talking 5-6 hour plus kind of runs. I think we've all seen these kind of demos, you know, of like companies being like, hey, we've like one-shotted a browser, for example, but not necessarily sharing like some of the details into what goes into the harness, and that's what we kind of want to talk about today. So the first half, my amazing colleague Andrew will talk about a little bit about basically how we've got here, some of the primitives that we've shipped in Claude Code, and you know where we are today. And then I'll hop back on stage to talk a little bit about some of the more experimental stuff that we're playing with harnesses, as well as a few examples of what we've seen. But over to you.
Sounds good. Thank you, Ash. And yeah, thanks everyone for joining first session of the AI Engineer Conference. So glad you're spending it with us. My name's Andrew. I'm on the Applied AI team based out of London, working as a solution architect with a lot of our digital native and industries customers. So yeah, I'm going to give a little bit of a history tour, trip down memory lane, but really with the focus on all the things that we've shipped that lead to agents being able to run for multiple hours or even days at a time. And then I'll hand over to Ash to do more of the state of the art. Right, okay, so a little quote on Twitter from Boris, the creator of Claude Code. This was on the 1-year anniversary of Claude Code, basically saying a year ago, Claude was struggling just to write bash commands and escaping strings. And it could run for maybe 20 minutes at a time. And then we're now at the point where almost all of Claude Code is being written by Claude Code, and it can run effectively for days at a time. So sort of a big swing over just the course of a year, and I'll walk through that history a little bit now. But just to, maybe I'll zoom in here, just to sort of frame the problem up, like why is it that it's really difficult for these agents to run for extended periods of time? I think broadly there's 3 big buckets. Some are more intuitive than others. So firstly, context. I think we all understand context windows very much finite. So you start a new session, there's like amnesia. The agent has to start from scratch, so you need some sort of memory components. Also, as you're working through a context window, there's this notion of context rot. So there's less coherence as you're getting deeper into that session. Also, you might get to the point where the model actually exhibits what's called context anxiety. So it gets kind of nervous as it reaches the end of its context window, and it just quickly hurries up to finish what it's doing. This kind of leads into planning. So in general, models are not that great at planning just out of the box. They might try and do everything in just one shot, or for example, they might build half a feature and then stop, or they might just run out of context altogether and sort of leave a half-finished app built. But then maybe less intuitively, models are really bad at judging their own output. So I know we all know that models can be sycophantic and sort of tell you what you want to hear, but this applies as well to coding tasks. So it might look at a feature and see that it's sort of half-baked or a little bit implemented and say, yeah, okay, that looks done, and then it'll move on to the next thing. Or it might build a feature like a button, but actually the back end doesn't exist for it. There's sort of nothing behind that, but it looks like the feature is done. So I know Ash will talk quite extensively of some of the new techniques we have to help with this specifically, so models can become better at judging their own output. So there's 2 ways really we can fix these things. The first one is obviously the model. So baking it all into the model weights themselves. And I'm sure you've all seen this meter chart. It's basically how long can an agent run for with a minimal scaffold where it's completing 50% of the tasks. And you'll see from Opus 3.7, it's around 1 hour, and up to Opus 4.6, 1 year later, it's at 12 hours, so an entire day. And we've, of course, managed to get that running much longer. Other people have as well, but this is just a sort of very minimal scaffold. The second thing that you can do is, of course, make changes to the harness itself. So this is the scaffolding around the model. And we have the agent SDK, which ships with all of the primitives that we've been building over time. So there's the core agent loop itself, where you have Claude model that's determining what to do, what tools to run. Maybe it's pulling in some tools from MCP servers. It might delegate some tasks to a sub-agent. It's bringing in all the context from things like Claude.md or the skills that are loaded or slash commands. There's a whole permission system. And this will change over time as well as the models get better and improve. But these are sort of the core primitives that we're working with. And then, of course, you use this framework to build your own harness for whatever it is you're trying to do, such as some of the things that Ash will show later on when we get into more long-running agents. I think what's also interesting is just looking back at the last year of releases is that when we've released a model, we've always also released a lot of harness changes alongside the models. So really these things are co-evolving together. So we'll just look back, I suppose firstly, just prehistory beyond 1 year ago. I think we all remember that period where Claude had the artifact section of Claude.ai, and Sonnet 3.5 was the first model that really showed promise when it came to coding, and it could now verify that. It could look at what it had built and sort of iterate from there, and that was quite an aha moment, sort of pre-Claude Code. But then also, we shipped computer use, so it could start clicking around, taking screenshots, testing its own code, as well as MCP spec, which enabled it to sort of use tools. So then getting into Claude Code. This is February 2025, so this was about just over a year ago. Sonnet 3.7 was released, and this was sort of state-of-the-art on SWE-bench, and Claude Code was released in research preview. And I think an interesting quote that I pulled from this release actually is that the goal of Claude Code was to better understand how developers use Claude for coding to inform future model improvements. So essentially when we released Claude Code, the whole idea was for it to be somewhat experimental to inform how we actually improve the base model itself. And you'll see this trend that over time the models become better, the harness, certain aspects of it might become less necessary or it will evolve. Just in terms of these slides as well, in the bottom left corner, these are some of the things that are sort of the focus of these releases, whether it's context or planning or verification, and then some stats, but I'm not going to sort of read everything. So yeah, next, this was around May time of last year, Opus 4 and Sonnet 4 were released. And just in general, these tools got much better at sort of managing their own context and getting to task completion without reward hacking or anything like that. And then Claude Code became GA as well, and we released the Claude Code SDK, so sort of the harness powering Claude Code. Little interlude here from the timeline. I think everybody now knows about this Ralph Wiggum technique. You might not know that it was actually last July that this came out when Jeffrey Huntley initially released the paper, because it really sort of gained a lot of traction around, say, December or so of last year when, for example, people started playing around with it themselves. Claude also released our own Ralph loop within the Claude Code harness itself. But essentially, it's quite sort of a simple technique that you're just taking a prompt and you're feeding it into Claude Code CLI, for example, and then you're just running that on a loop until all the tasks are complete. It's a little bit deeper than that. I think people tend to simplify it. There's actually a few phases where it first would have some kind of planning where it breaks down that prompt into a few different features, and then it would pick sort of one task from that and start a new session and then work with a fresh context window. So a lot of those concepts were applied in the Ralph loop, but I think why it caught so much attention is because it sort of seems really simplistic. And he put it deterministically bad in an undeterministic world. So the idea being that it's better to fail predictably than it is to succeed unpredictably. When we actually created our own plugin for this in Claude Code, you'll see, well, I don't know if people can recognize what the major difference is. There's some people say, that's not a real Ralph loop. The idea is that this is just running within a single Claude Code session. So it's not creating a fresh context window. It's just relying on compaction to happen over time. So maybe it's not considered sort of a real Ralph loop, but you'd set the max iterations, you'd set a safe word, and then essentially a stop hook would intercept when Claude would typically stop. And if it's not finished, it would just sort of continue until it hits one of those exit criteria. OK, so on to Sonnet 4.5. This was when the model just generally started getting better again at handling its own context. So this is when it became more context aware, tracking how many tokens had been consumed. So as it got towards the end of the context window, it sort of understand that, and it could manage its own context. Claude Code 2.0 also shipped. This is where we introduced checkpoints, so actually keeping track of the code over time, being able to rewind to previous parts of the session. And then we just sort of renamed the Claude Code SDK to the Agent SDK. And that's because we realized it's much more general purpose than actually just for coding. So you'll see we're talking about coding a lot right now, but I think what's very interesting is applying these long-running harnesses to other domains as well. At this point, we could run for about 30 hours or so with Claude Sonnet 4.5. But then completing the family with Haiku 4.5 and Opus 4.5, this is where it got really interesting because all of a sudden running many sub-agents became really economical, and Opus 4.5 became really good at planning. So we could start doing things like using Opus 4.5 for planning, and then using Sonnet 4.5 as the workhorse for really executing all of that code. And then there's a big couple months as well, because this is when we released Skills, which again, very good at making effective use of the context with this notion of progressive disclosure. So just the front matter of the skill is loaded in instead of sort of all of your tool descriptions, which can consume quite a lot of the context window up front. And then sort of the entire rest of the body of the skill is loaded in if it's instantiated, followed by, say, some references to even code that could run more deterministically. And then more context improvements, things like programmatic tool calling. So instead of running a bunch of tools, pulling all of that into context, and then trying to process it, actually just writing code on the fly and being able to sort of run a series of tool calls and then just get the final result back. And again, this is all just to improve the usage of the context window. Okay, so a lot going on this slide. But at this point, this was around November time, we released our first blog post on long-running agents and how you would go about building these. So a lot of the concepts I've already described should make this fairly easy to understand, actually, where, say, a human would write something like, write me a browser, or create a Slack clone, or a Salesforce clone, just something like really, really vague. And the first thing that would happen in this harness that we built is there's an initializer agent that would take that simple prompt and it would break it down into a series of persistent artifacts. The first being a feature list of, say, X number of features. Featurelist.json, because we actually found the models might overwrite markdown files, whereas they're less likely to just overwrite JSON files, which is kind of interesting. It would also write a progress file, of course, sort of start the Git repo, build an init script, and then just have a flag for whether the features are complete or not, if they sort of pass all the tests. From there, it would go into this harness loop where there's multiple different steps here. So the first one is, again, in a fresh context window, just getting the bearings. What's the present working directory? What's the progress file say? Okay, and then doing a smoke test, so running the init script, so it didn't have to figure out how to do that every time, get the server up and running, et cetera. And then picking one feature, only one feature that hasn't passed all of the tests, implementing that feature, doing some actual tests, so verification loop, much like a human would do using Puppeteer in this case. And then if everything passes, actually writing the git commit and changing the state of this particular feature to passes. And then if there are any features that are unfinished, just continuing that loop in a fresh context window. So we're starting to layer in a lot of these concepts here, fresh context windows, these sort of persistent artifacts, verification loops, really good planning up front. You'll see like this is sort of the first iteration of these long-running harnesses here. Okay, so continuing with the history tour, so then Opus 4.6, Sonnet 4.6. These models are really great because Sonnet 4.6 was basically offering that Opus level intelligence more at the Sonnet price, and it became, again, like very much a workhorse for a lot of Claude Code. And Opus 4.6 just became really good at planning. We called it like very much an agentic model. So Opus 4.6 was great at deciding like which tools to use and just being able to run for much longer. If you recall that meter chart, you'll see that this was a jump from about 4 hours up to 12 hours with sort of that very simple harness. So this model is like very, very agentic. And then along with that, with some of the research we had done, we released agent teams, which the idea being in Claude Code, this sort of more general purpose way for you to, say, scaffold out your own set of custom agents. And the innovation with agent teams is that instead of everything reporting back into the main agent, the actual sub-agents could communicate with each other. So they sort of had their own way to coordinate and then report back to the main agent only when it was required. We also introduced server-side compaction, which basically meaning that these models can now just run indefinitely and compaction could just sort of happen on the server side. And then this 1 million context GA. So now we have like one big context window. You see like the models are getting better. Maybe you can just run a lot within a single context window even instead of necessarily needing new sessions all the time. You see how things start shifting over time. So that's sort of the whole overview. You can see all of the different releases that I shared here on this table, and you can see how it's changed from, say, Sonnet 3.7 at 1 hour to 12 hours with Opus 4.6. And then we have our own anecdotes as well, where tasks would take, say, like 20 minutes when it was Opus 3.5, and now we're building, say, fully fledged apps that you don't have to run for 30 hours. They can run, typically we're seeing like, say, 3 to 5 hours. You can build like a really, really fully featured application that runs out of the box. So what's really interesting is the harness doesn't just disappear as the models get better. It's really evolving as the models change over time. And it's really fascinating to sort of find the gaps in the model and then fill that in with the harness. And then you train the model on using that aspect of the harness. Then maybe at some point you actually remove that entirely. And sort of this iterative loop just keeps happening over time with more and more of these sort of co-releases that we have. So yeah, hopefully that was an interesting little trip back through the Claude evolution and how it applies to the long-running agents. And so I'll hand over to Ash to continue with where we are today in terms of the state of the art.
All right. Quick question. Any of you guys have any agents running at the moment in the background doing work while you're here? Just 1, 2, 3? Okay. Probably should be more of you. Hopefully by the end of this, you'll have some ideas to like take away and actually like put into practice. So yeah, that's the history. And I quite like that quote that Andrew talked about, where the frontier doesn't really shrink, it just moves. And so what I wanted to talk about a little bit is some very simple kind of harness patterns that we've been playing around with internally that we use to build these like very fancy one-shot demo apps. But also, we're experimenting with this stuff in post-training in RL. How do we make our models and just their general behaviors more adept at autonomous work? So if you've ever tried to get an agent to try and review its own PR, you'll kind of understand where this is going. So this general idea is shamelessly kind of stolen from GANs, generative kind of adversarial networks. So you have this generator kind of model, and then you have some sort of discriminator, and you have some sort of adversarial pressure between them. The generator builds, the evaluator grades, and the whole idea here is we're splitting up, the context, windows, system prompts, the jobs entirely, right? The evaluator here isn't just reading diffs, but it's actually using Playwright to open live pages, click around, try things out, and then it eventually hands back whatever critique it's decided back to the actual generator, and you kind of continue that loop. Contrast that with what most people today are doing, which is kind of using one Claude Code session, telling it to check its own work, and kind of loop that way. So the obvious question for me, at least, is if the evaluator is also just an LLM, why doesn't it just rubber stamp it too? And so the key idea that we're kind of exploiting here is, yes, the evaluator is still a large language model, and yes, it's still going to be biased towards liking large language model style outputs, but tuning a standalone critic to be harsh is actually very tractable. but tuning a builder to be somewhat self-critical is not. I think a really good analogy for this, right, is same as humans. It's very easy for me to, critique a lovely piece of artwork or, a fine meal. Much harder for me to actually go ahead and paint that or cook that meal myself. So what we're doing here is exploiting the gap between the ability of an LLM to be kind of a critic versus a generator. So the next thing I kind of want to talk about is how do you actually think about designing these critics? It's very similar to the process of creating good evals, but in the context of full stack apps, there are a lot of fuzzy kind of areas which go into what makes something good. It's not just does it work, but does it look good? Does it feel good? Is there an element of taste in these kind of products as well? So this is where we've been doing a lot of experimental work, especially when trying to imbue Claude with design taste and post-training, but also create these kind of front-end design skills that we kind of put out there and just generally improve the front-end design ability of our models. So the way we think about this is most people say you can't grade taste, but we think you can if you have a strong enough opinion on it and you just kind of write it down. And so the way we do this, at least, is with kind of creating a rubric with 4 criteria: design, originality, craft, and functionality. We actually weight this towards design and originality. We've kind of shifted the weightings between these 4 things depending on which model's in play. But at the moment, Opus 4.6 is pretty good at functionality already. So the problem that we're trying to overcome is how do we prevent things like, purple gradients, general kind of AI slop type aesthetics in general. And we kind of just go ahead and calibrate this with a few short examples on reference sites, so the evaluator's kind of taste converges on our own. And let me show you an example, I guess, of what this actually looks like kind of in practice. So this is just an example of a model going through this similar kind of loop: generator, evaluator launches playwright, navigates, screenshots, scores on those kind of 4 criteria, writes critique, and then hands back to generator. So all of these examples are just HTML and CSS only that I've gone through for maybe 4 hours, 5 to 15 rounds. I think the interesting thing here, which is quite unique and something which you wouldn't necessarily get if you're just using a single kind of agent loop, is that the thing pivots, right? So imagine the generator gets stuck on one of the 4 criteria. Let's say it's really struggling and constantly scoring low on originality. This kind of GAN-style harness, which we're using, will just throw the whole thing out and try again from scratch. Whereas in a single pass generation or a Ralph loop, it keeps trying to patch the same thing. And this kind of ability to kind of course correct over very long kind of time horizons is something which is quite unique to kind of breaking down the different roles that go into building something. So that was just an insight into, I guess, how we think about the front-end component. But how to go from kind of just nice pages to fully working apps, we added one more role, a planner. And so, again, sounds very simple. It's ultimately just taking kind of a one-line prompt and then breaking it down into a very deliberately high-level kind of spec. So what it does is actually just spec the granular, it kind of specs the general workflow into a series of sprints. What it doesn't do, and what most harnesses do today, is necessarily try and plan the granular technical details of the product. The reason being is, one, it's very likely to still make an error, but when it does make an error, it's going to cascade through every single one of these sprints and kind of magnify errors over a multi-hour time horizon. If you kind of squint at this, this is kind of just, a very simple kind of PM, IC, and QA kind of org structure, right? We didn't invent this, we just kind of gave each role its own kind of context window. And the bit which is kind of interesting, I think, to talk about is the glue between the generator and the evaluator in this kind of setup. So before the generator actually goes ahead and writes a single line, we have the two agents basically negotiate what done actually means. And so let's say the generator proposes, I'm going to build X feature, and you should verify it by testing Y. The evaluator might push back and be like, actually, the scope is too big, and those tests that you propose are a bit too weak, and you've missed XYZ edge case. And you basically have this back and forth via files on disk. One writes the markdown, the other reads it, and you iterate until both agree. And then once you kind of reach that kind of condition, then you actually start building. And then the evaluator kind of grades against the contract that those two agents have decided between themselves, not the original spec, which the planner has kind of one-shotted at the beginning. And why this matters, as it kind of bridges this kind of idea of kind of user stories, i.e. the spec, and kind of converts it into slightly more tangible, testable kind of assertions, some sort of contract, without the planner having to over-specify kind of upfront. And I think this is kind of the key innovation that the Ralph loop never really had. It had a kind of fixed plan, .md style kind of thing, but nobody on the other side is necessarily arguing with kind of the main loop. And again, it comes back to like having these separate context windows and adversarial pressure. So let me show you an example of a very simple prompt that we had in a solo kind of loop versus the harness that we just discussed. So the prompt was basically build a retro game maker, and that was it. And I'm not, gonna try and convince you that this is like necessarily the most cost-effective or most efficient way to try and build an app. As you can see, one, it takes at the moment an extremely long amount of time. Two, it's very expensive. But also, as we'll see in a second, a lot of the stuff actually starts working only with this harness when it didn't in a kind of a solo loop. So this is what it kind of looked like, the opening screen, at least when we didn't have the harness. Pretty simplistic, a little bit boring, but it still looks nice, right? If this were the whole app, you'd ship it, but it's kind of the bait, I guess, if you will. This was kind of the sprite editor, if you will. Again, it still looks fine. The canvas is there, the palette, the frame timeline, live preview. Maybe it's a little bit cramped, and the color picker is just black swatches, but it kind of works. Clearly, the agent actually did understand what it was trying to do. And then the one thing that you actually has to do, which is play mode. Entities rendered, score, health, all the other things which go into an actual game. Pressing an arrow key does nothing. Pressing a space key did nothing. The agent really didn't have any idea how to test itself, what it actually meant to play a game and actually succeed. And yeah, this is kind of the same prompt, same model, and this is kind of the breaking point. It kind of looks down on the surface, but when you try and actually push it to its limits, it just kind of failed. And then if we ran the same prompt with the same model, this is kind of what it looked like when we ran the harness. So this was about, $200, 6 hours. First up, it decided to name itself RetroForge. It decided to create a new project dialog, have a very nice canvas. None of that was in our prompt. So this was all the planner deciding okay, here's what the product decisions should look like, and then the two other agents deciding, right, how am I going to test this? If we look at the sprite editor, we have kind of a full 54 color palette, the kind of 8-bit preset from the project dialog flowing through. You see the sprite at actual game scale. It's a lot more complete as a product in general. We had a whole new kind of AI level assistant. This is where it's kind of started to get recursive. The planner had decided, right, we should have some AI features, which is just a vague line in the spec. And the harness turned that into a full AI level assistant inside the app that it was building. So, someone could come in and say, hey, create a castle with sprites guarding it, let's say. This is something which the solo ROM would never even attempted to look at. Without a planner, that phrase just becomes like a work item to look at. Then finally, I guess, the actual results kind of applied. So play mode, you had this whole debug HUD in the top left, which you can clearly tell is to make life easier for the evaluator, for example. Those numbers are live. The physics loop is actually running. Arrow keys work. The player moves. Collide with Castle Wars. Because the evaluator actually launched the game, tried to play it, knew necessarily like what features needed to be tested to make this game kind of real and successful. And the difference between this output and the previous output is entirely just scaffolding. And it's a very simple loop ultimately, but the results are quite startlingly different at least. And so, in case you're curious, the kind of things which the evaluator did catch are pretty basic kind of stuff. It's things like, fast API route ordering, passes every unit test but might actually break in prod. The evaluator catching things like the delete key, having some kind of Boolean logic bug. Again, these are things which were only caught because the evaluator is actually using the app. It's things which might get through CI in a Ralph loop, but this isn't, that level of specificity isn't something which happened by accident. And so this is the kind of level of detail which these models are kind of going to at this point in time. So we talked about the kind of contracts that the generator and the evaluator would write between themselves. For this app, it decided that there were 27 contract criteria. That's a level of granularity which we found that you really need to make findings kind of actionable. If you have vague criteria, you have vague critiques, the generator just kind of shrugs and does things. Whereas if you have granular criteria, the agent knows, okay, I need to fix this exact line. What's kind of interesting, I thought, and I want to be honest about this part, is that out the box, Claude is a really, really bad, just general QA agent. Andrew talked about this a little bit in his bit, right? But the same kind of sycophancy and generosity bias that everyone hits with general LM as a judge systems also applies here. Most of the time in early runs, it would, the QA agent would kind of find a bug and be like, fix it later, might take 2 weeks, and then just kind of like be done with it. So we actually had to spend an exorbitant amount of time like going through, trying to tune, small layout bugs, edge cases, and kind of feeding that into the prompts. I wish there was some kind of secret to actually doing this, but realistically, the whole kind of art to building this system and making it good was kind of reading the traces. The primary debugging loop was this, and not necessarily running more experiments. It was reading what the agent actually did, finding where its judgment diverged from ours as humans, and then tuning the prompt for that. It was the same kind of muscle as reading kind of a stack trace. One kind of tooling tip that we had was kind of piping agent transcripts into files, kind of grepping them with another agent or having another agent kind of go through them, and then kind of update the prompts itself. So you have some sort of like closing the loop even on just like building this harness out. So the last thing I kind of wanted to talk about was how to think about adjusting your harness as these models kind of get better in time. I think there's a lot of like discussion around whether harness design is kind of dead or null, especially with models that, I mean, when I wrote this, it was just Opus 4.6, but even like Mythos, level models. And I think the key thing that we noted is it's really important to get a feel for what the kind of spiky behaviors of any individual model are, and then try and adapt your harness to kind of fill the gaps. So Andrew talked about this a bit, but context resetting between sessions. We kind of dropped that entirely. Opus 4.5 used to have really bad kind of context anxiety, whereas Opus 4.6 just didn't as part of post-training there. And so one continuous session in compaction was more than enough to handle very long sessions. Sprint decomposition. We don't have a very strong opinion on this, but it was something which was really, really critical to getting Opus 4.5 to work. But Opus 4.6 was able to kind of hold a 2-hour continuous build coherently in a way without necessarily having to be force-fed one feature at a time. The cadence at which the evaluator should run. Previously, we were running it every single sprint per se, whereas now we were just running it at the end of a one-shot generation from the model and then passing back. So the harness is still the same, we're just kind of simplifying the specific kind of loops and the kind of the recipe that kind of goes into it. The lesson isn't necessarily our harness was wrong, but rather it was right for 4.5, the frontier moved, and we ran a simplified version to see how it worked. So this is kind of what the final kind of setup kind of looks like today. Having that planner, generator, evaluator loop is still the kind of core of our system. But you can see we kind of ditched a bunch of the other kind of components that made this slightly more complicated than it had to be. We also, as kind of mentioned, big fan of just using a file system for shared state instead of kind of leaning on context windows for very long-running agents in general. And this is an example of the simplified harness running with one of our latest models. Again, very, very expensive, but you can see it's actually roughly like half the cost of the previous runs, just because we're kind of doing things in a slightly more simplified manner, but it's still running over a very extended period of time. And so this is an example of a DAW, which is basically just like a music creating app, if you will. The agent sets the tempo, a key, it lays down the melody, it builds the drum tracks. This is the evaluator actually going and testing the app itself. We did actually listen to like the music in this. Obviously, Claude can't hear at the moment, and so the music was pretty trash, but the app was really good in general and pretty fleshed out, which, you know, a model ago, this is something which would never have worked. But this is something which was possible with just a couple rounds. And this is kind of that meter curve, which Andrew was talking about, kind of really in action. And so I kind of wanted to close just by saying, you don't necessarily need, you know, our internal harness to go away and start thinking about this. We are constantly trying to ship bits of, you know, these primitives into Claude Code directly, but also there's nothing stopping you from just going ahead and building something similar to this kind of on your own. So we just shipped, you know, auto mode is probably my favorite thing for slightly more, you know, safe YOLO, if you will, instead of running dangerously skip permissions all the time. We already have custom subagents as a primitive, right? Your evaluator, your QA role, give it a harsh system prompt and a very detailed rubric. Playwright MCP or Claude for Chrome MCP, already extremely good at web app stuff, or just use compute use if you're building kind of native apps. And skills, again, a very nice way to package your kind of grading rubrics into your kind of general development flow. So yeah, 5 things if you're kind of taking a photo. This is the slide I would say to kind of remember. Self-evaluation, very much a trap. Just use an adversarial evaluator. Compaction doesn't necessarily, does not equal kind of coherence, right? Lossy summaries really drift. Structured handoffs and clean context are a very good pattern that we've seen. Don't think that subjective quality isn't gradable. If you have a strong view on what something should look like, then kind of force yourself to write it down. We found this made kind of a really massive difference to the quality of kind of apps that a model was able to generate. And then kind of finally was really just, you know, sit with the model, read the traces. Only then can you kind of really know what bits of a scaffold to delete, what bits to keep, especially as the kind of frontier moves. But yeah, that's it from me.